Welcome back and welcome to lecture 5 in our course Analysis of a Complex Kind. Today we'll talk a little bit about topology in the plane. Topology is the study of shapes, and we need to name some shapes and find out how to write them down in complex notation and learn about some concepts of topology in order to move to some really neat applications next week. So let's start with something very simple. Circles in the complex plane. A circle needs a center and a radius. So let's call the center z0 equals x0 plus I y0. So suppose we wanted to write down a circle of center z0 and of radius r. The inside of that circle, we'll call that a disk. So this inside here is the disk of radius r, centered at z0. And the circle itself, we'll call that the circle, so that's the boundary. So by BR of Z0, we denote the inside, the disk of radius R centered at Z0, and KR is the actual circle. So Z has distance less than R from Z0, or Z has distance R from Z0. That's kind of long to write. Is there any better way to write down what the distance is between Z and Z0? So how do we measure distance in the complex plane? Let's draw a picture. Suppose I have a point Z0 with coordinates x0 plus I y0 and another point Z with coordinates x plus iy. And I wanted to find the distance between these 2 points. In particular, I want to determine whether this distance is at most r or equal to r. So what do I know? I know this is x0, and this is the x-coordinate x. And similarly, I know this is y0, and this is y. What is the distance between z and z0? It's the length of the connecting line segment between z0 and z. How do I find that? Well, I can draw a right triangle here. And I find a triangle with this right angle. And so in order to find this distance, I'll call that d, I could just as well find the length of the two legs and use the Pythagorean theorem. So how long are these two legs? Well, this leg down here has length x minus x0. Because that's the distance between the two x-coordinates. And this leg here has length y minus y0. So in order to find the distance d, I can use the Pythagorean theorem and find that d is equal to the square root of the sum of the squares of the two legs. So the square of x minus x0 and the square of y minus y0. But that looks awfully like the modulus of a complex number, namely the complex number x minus x0 plus I times y minus y0. That's how we would calculate its modulus. And this complex number is really the complex number z minus z0. So this distance d is actually the modulus of the complex number z minus z0. And with that new notation, I can write down the disk of radius r centered at z0 in a much easier way. It's the set of all those z's for which the modulus of z minus z0 is less than r. And the circle of radius r centered at z0 is the set of all z's for which the modulus of z minus z0 is equal to r. We need some more definitions. Suppose we're given a set E, so some set. Maybe it looks like this, maybe it has a hole, who knows. We say an interior point of E is a point like this, point z0, such that there exists some r, such that the disk of radius r centered at z0 is entirely contained in E. So I can draw a little disk around this point, and it still fits entirely into the set E. So obviously, if I try to do that out here, so if I try this point, like no matter how small the disk I draw, it's never going to be contained in E. But even a point like this, if I draw a disk around it, some part of that disk will always stick out. Or a point right here on that edge If it's right on the edge, no matter how small I draw the disk, it'll always stick out. So interior points are points that are really inside of E, and there's some room, some buffer room before I really hit the end of E. So those are interior points of E. Points like this are called boundary points of E. So a point B is on the boundary of E. If every disk that I draw around it contains some points in E, so those are two good ones, so I did meet some points in E, but also some points that are not in E. So no matter how small I choose this disk, I will always capture some points in E and some outside of E. Those points are called boundary points of E, and the boundary is denoted with this funny new Greek symbol that we had not introduced before. It's like a delta symbol almost. So that's a symbol for the boundary of E. We say that a set is open if every one of its points is an interior point. And on the other hand, we say a set is closed if it contains all of its boundary points. So those are actually quite subtle definitions. So we need to look at some examples to understand those a little bit better. So the ball of radius r centered at C0 is an example of an open set. Let's look at that. A disk centered at a point C0 and of radius r. I'm claiming that's an open set. So no matter which point you pick, I can always find a little disk around that point. It still fits into the original big disk, even if it's really close to the edge. I can't be on the edge because points on the edge are not included in my disk of radius r because I require the distance between z and c0 to be strictly less than r. So no matter where I am, I'm not quite on the boundary. And so there's always room for a little disk around it without hitting the boundary. Also, everything out here is also open. All those points for which z minus c0 is bigger than r, that's also open because I can find for any point a little disk around it that stays entirely outside of the disk of radius r. The whole plane is open. Well, you know what, every point is interior point in the whole plane because no matter where I put a point in the plane, I can find the disk around that, it fits into the complex plane. So that's kind of trivial. The empty set being open is a little funky, but the empty set doesn't have any interior points, and so it contains all of those. So that's a little bit of a mathematical technicality that the empty set is also open. Now, here's an example of a closed set. The disk of radius r, but this time instead of writing strict inequality, I made it a less than or equal to. So I did include these boundary points. Now, now it's a closed set because it's the disk together with all of its boundary points. So this includes all of its boundary points and it's a closed set. The circle itself is also closed. There's no extra boundary points. No other point would be considered a boundary point. So it's okay for us to look at the boundary in a more intuitive fashion. We're not going to prove any of these facts. I want you to get an intuitive understanding of what it means to be open, closed, and what the boundary is. This one is kind of unsettling. The plane itself is also closed. It doesn't really have any boundary points, and because it doesn't have any boundary points, you could say it contains them all. Again, that's a mathematical technicality. The empty set is also closed because it contains all of its boundary points. It doesn't have any points, so it doesn't have any boundary points, so it contains them all. Again, we're being a little nitpicky, but technically the whole plane and the empty set are closed. So those are sets that are both open and closed. That is unsettling because open and closed in mathematics are not quite the same as open and closed for a door or for a drawer. A door can be open or it can be closed, but it can't really be both open and closed at the same time. Sets in the complex plane or sets otherwise can be both open and closed, and there are even sets that are neither open nor closed. Open and closed is not the same meaning as it has in our daily life language. Here's a set that is neither open nor closed. The set is the disk of radius r centered at C0, but now I'm including parts of the boundary, but only those parts for which the imaginary part of z minus C0 is greater than 0. So I'm looking at this disk of radius r centered at a point C0. That's this first set. And then I'm including those points on the boundary for which the imaginary part is greater than 0. So these points are also part of my set, but these points down here are not. And so since not all boundary points are included, the set is not closed. But it's also not open, because for points up here, I cannot find a disk around such a point that is entirely contained in my set, because part of it will always be sticking out. The terminology of open and closed is a little bit tricky, but that's all right. We just want a vague understanding of what open and closed means. You don't have to have a perfect understanding for this course. We can force a set to be closed by closing it. And to do so, you take the closure of the set. The closure of a set is the set, and you just throw in all of its boundary points. So if you're missing some boundary points, you're adding them in right here. So the closure of a set denoted by a bar on top of the set, kind of similar to our complex conjugate bar. So the closure of a set is the set together with all its boundary points, and then by definition it has to be closed. On the other hand, we can force a set to be open by just taking away stuff from it. The interior of a set, denoted with a little circle on top of the set, is the set of all interior points. So we're taking away points that were not interior points. And examples again, the closure of the disk of radius r centered at C0 is the disk of radius r centered at C0 together with a circle. So we're adding in all the boundary points. The closure of the circle is the circle itself, because it already contains all of its boundary. No extra boundary points could be added to it, and so there's nothing that we have to do. If I were to take the disk of radius r and take its center away, and then take the closure would bring that center back in, because it would have been a boundary point previously. So that center comes back in, as does the boundary. If I look at the set of all z for which z minus c0 is less than or equal to r, so it's kind of the disk together with a circle, if I want to take the interior of that, I would throw away the boundary points, and I get the disk of radius r back. On the other hand, if I start only with a circle, the circle of radius r does not have any interior points. There's no point on a circle of radius r that I could find around which I can find a disk that actually fits into the circle. There's always stuff outside of the circle in there. And so it has no interior points. So the interior of that set is actually the empty set. We also need the notion of connectedness. Intuitively, a set is connected if it's kind of in one piece. But if we want to do mathematics with this, we need to have a more precise definition. So how do we make this more precise? Well, it turns out being connected is difficult to make precise. So we first make it precise what it means to be separated. We say that two sets in the complex plane are separated if there are disjoint open sets U and V, such that one of the sets, say X, is contained in U, and the other one is contained in V. Disjoint means that these sets have nothing in common. So U intersect V is equal to the empty set. That's what it means for these two sets to be disjoint. Before we even continue with this definition, let me give you an example. Suppose we're looking at the set X, which is the interval from 0, and 0 is included, to 1 with 1 excluded. And Y is the set from 1 to 2, 1 excluded and 2 included. Then these sets, I claim, are separated because we can find open sets U and V that are disjoint and contain U and V. So, for example, U could be the disk of radius 1 centered at the origin. This set U contains all of X. Because that boundary point here was not part of X, I'm not missing anything. So that's an open set that contains all of X. And on the other hand, the disk of radius 1 centered at 2 contains all of y, and they don't intersect. They kind of seem to touch there, but because they're open disks, they actually have nothing, no point in common. So I found two open sets that contain x and y. They have nothing to do with each other. And that makes x and y separated. Now we say that a set is connected if it's impossible to find two separated non-empty sets whose union equal to W. So if I cannot find such a way of separating my set, then it's connected. So in particular, in this example, x union y, which is really the interval from 0 to 2, but we're missing the point 1, is not connected because I can separate it. So it seems to be easier to check whether a set is not connected, but it is hard to check whether a set is connected. For open sets, thankfully there's a much easier criterion to check whether or not the set is connected. This is only true in the complex plane though. So here's a theorem. We're not going to prove this theorem, we'll just use it. Suppose G is an open set in the complex plane. This set is connected if and only if any 2 points in G can be joined by successive line segments. So if I draw a set here, and the set could have some holes, so maybe it has a hole right here, and it has a hole here, and maybe it's missing some stuff there. But it's an open set, and it's connected if I can join any 2 points via successive line segments. Suppose I'm picking 2 random points, this one and that one. So can I join them with line segments? Well, yes, I can. I can just start drawing and go turn whenever I need to. And I made it. So I joined them in G, so I never left my set G, and I joined them with line segments that never left G, and therefore this theorem tells me, if I can do this for any 2 points in G, that my set G is connected. On the other hand, if G consisted sort of several parts, and I picked one point over here and another one over here, and I now tried to connect them with line segments, I would kind of have to get across, and that's leaving my set. So this set, G here, is not connected, whereas this one is connected. Finally, we say a set is bounded. Well, it kind of finishes, stops. So if there exists a number R such that the set is contained in a large enough ball of radius R. So let's draw a complex plane here and some set, and it could be a complicated set, but it stops going out toward infinity kind of. So if I choose a large enough radius, and it has to be pretty darn large radius, but I choose a large enough radius, this is a circle of radius R centered at the origin, eventually my radius is large enough so it'll contain that set. On the other hand, a set for which I cannot find such an R is called unbounded. So what are examples of unbounded sets? Here's one example. Suppose I take 2 radial segments, and A is the set between these 2 radial segments. Well, that keeps going and going and going and going. No matter what radius I choose, I'm just not going to capture it all because it just keeps going. So this set would be an example of an unbounded set. Another example of an unbounded set is a whole half-plane. Let's say all those points for which the real part is positive. That's an unbounded set. The whole complex plane itself is an unbounded set. So there are plenty of unbounded sets. We already brought up this notion of infinity a little bit for those unbounded sets for which they're kind of reaching out towards infinity. In R, we remember there are 2 directions that give rise to infinity. I could go in the positive direction and go towards plus infinity, or I could go in the negative direction and go towards negative infinity. So, 1, 2, 3, 4, 5, walk out towards plus infinity, and -1, -2, -3, -4, -5, they go toward negative infinity. So we have a plus infinity and we have a negative infinity. In the complex plane, there's only one infinity. We regard infinity as no matter how you get there, if you leave any bounded set, you're going to get toward infinity. So there's lots and lots of ways of getting there. So 1, 2, 3 is one way of getting toward infinity. Or -1, -2, -3, -4, -5, that also goes toward infinity. But you can also go on the imaginary axis, or on the negative imaginary axis, or you could even go in circles. So 1, 2i, -3, -4i, 5, 6i. So this sequence would also run off towards infinity because it leaves any bounded set. So as soon as you leave any bounded set, we're going toward infinity. So infinity is sort of all out here. Outside of large disks, we're getting closer and closer to infinity, no matter in which direction I go.